Hi everyone, in this video, we're going to walk through a titration problem where we titrate cocaine, a weak base, with nitric acid, which is a strong acid. We'll calculate the pH at different stages of the titration. First, we're going to cover everything up to the point before any acid is added. That's when volume of acid added equals to 0 ml. Before we start calculating the pH, let's figure out of an important value, which is the equivalence point. The equivalence point is the volume of acid needed to completely neutralize the base. We calculate it using the formula M1 V1 equals to M2 V2, where M1 is the concentration of the base, which is 0.100 molar. V1 is the volume of the base, which is 100 mm. M2 is the concentration of the acid, which is 0.200 molar. And V2 is the volume of the acid we want to find. Now, let's substitute all the information we got from above into the formulas, and we'll find that our volume of acid is equals to 50 mm. So, the equivalent point is reached when we add 50 mm of nitric acid. Let's focus on the first condition, before any nitric acid is added or before titration. At this stage, we only have a solution of cocaine, which is a weak base. That means it partially reacts with water, like this. This reaction produces hydroxide ion, and those are what make the solution basic. Next, we are told that the volume of cocaine solution is 100 mm and its concentration is 0.100 molar. The Kb value for cocaine is 2.6 times 10 to the power of -6. We're going to use these values to calculate the pH. Next, we'll be using the Kb expression. The formula for base dissociation is Kb equals the concentration of hydroxide ion squared divided by the concentration of the base. Now, we plug in the values. Multiply both sides by 0.100, take the square root, so the concentration of hydroxide ion is 5.1 times 10 to the power of -4 molar. This tells us how basic the solution is. Finally, we calculate the pOH using the formula pOH equals negative log of concentration of OH minus. After we plug in the number, we find that the answer of pOH equals to 3.29. Now we got our value for pOH, we can finally calculate our pH value using the formula pH equals to 14 minus pOH, and we get our pH values equals to 10.71.
The next step is addition of the titration into the analyte. The titration is the nitric acid, and we will calculate the pH of the analyte after several addition of the nitric acid. First is the addition of 10 ml nitric acid into the analyte. In this step, we will use Henderson-Hasselbalch equation, which is pOH equal to pKb plus log conjugate acid over base. We represent the conjugate acid as cocaine positive, and we represent the cocaine as the base. To find the concentration of the cocaine, which is the base, we use the formula molarity times volume of the cocaine minus the molarity and times the volume of the nitric acid divided by the total volume. Thus, we get the concentration of the cocaine, which is 0.0727 molarity. Next, we move on to the calculation of to find the concentration of the conjugate acid, which is cocaine positive. We use the formula molarity times volume of the nitric acid over the total volume, and we get the value is 0.0182 molarity. And then we put the value into the formula of the Henderson-Hasselbalch equation to find the pOH. Thus, the value of pOH is 4.98, and to calculate the pH, we use the formula 14 minus pOH. Thus, the value of the pH is 9.02. We move on to the after addition of 20 ml of nitric acid. The concentration of the cocaine is 0.05 molarity. The concentration of the cocaine positive is 0.033 molarity. The value of the pOH is 5.40. And the value of the pH is 8.60. We move on into the after addition of 25 ml of the nitric acid. The concentration of the cocaine is 0.04 molarity. The concentration of the cocaine positive is 0.04 molarity. Thus, the value of the pOH is 5.58 and the pH is 8.41. Move on to the after addition of the 30 ml of nitric acid. The concentration of the cocaine is 0.031 molarity. The concentration of the cocaine positive is 0.046 molarity. The value of the pOH is 5.76 and the value of the pH is 8.24. Next, we move on to the after addition of 40 ml of nitric acid. The concentration of the cocaine is 0.0143 molarity. The concentration of the cocaine positive is 0.0571 molarity. The value of the pOH is 6.19 and the value of the pH is 7.81. Move on to the after addition of the 49 ml of nitric acid. The concentration of the cocaine is 0.00134 molarity. The concentration of the cocaine positive is 0.0658 molarity. And the value of the pOH is 7.28 and the value of the pH is 6.72. And then the last part is after addition of 49.9 ml of nitric acid. The concentration of the cocaine is 0.000133 molarity. The concentration of the cocaine positive is 0.0666 molarity. The value of pOH is 8.28 and the value of the pH is 5.72. And then we will summarize the milliliter of the titrant and the pH in the form of table.
Let us now proceed to the explanation of the over-titration phase in this titration. After the equivalence point, which is reached at 50.0 milliliters of nitric acid, the solution contains only the conjugate acid of cocaine. Any additional nitric acid added beyond this point introduces excess hydronium ions, as nitric acid is a strong acid that fully dissociates in aqueous solution. This causes the pH of the solution to decrease significantly and rapidly. For example, if 0.1 milliliters of nitric acid is added beyond the equivalence point, the concentration of excess hydronium ions is calculated using the formula concentration equals molarity times volume over total volume. This gives us a hydronium ion concentration of 1.33 times 10 to the power of -4 molar. Hence, the pH is 3.88. When 1.0 milliliter of excess acid is added, the concentration of hydronium ions become 1.32 times 10 to the power of -3 molar. This results in a pH of 2.88. Finally, for an over-titration of 10 milliliters, the concentration is 0.0125 molar. Thus, the pH is 1.9. This calculation clearly demonstrates that even small amounts of excess strong acid result in a large and rapid decrease in pH after the equivalence point. Based on the graph of pH against volume of nitric acid added, the titration curve begins at a high pH of 10.71, indicating the basic nature of the cocaine solution. As more nitric acid is added, the pH gradually decreases, forming a buffering region. A sharp drop in pH is observed near the equivalence point at 50 ml, where the pH reaches 4.79, indicating complete neutralization of the base. After the equivalence point, further additions of nitric acid causes a rapid and steep decline in pH, reaching as low as 1.9 at 60 ml. This overall pattern reflects the typical behavior of a weak base strong acid titration. For question 1, part B, we were asked to suggest a suitable indicator based on the titration curve obtained in part A. As calculated earlier, the pH at the equivalence point is approximately 4.79. An ideal acid-base indicator should have a color transition range that includes this value to allow for clear and accurate observation of the equivalence point during the titration. The most suitable indicator in this case is methyl red. This is because methyl red changes color between pH 4.2 and pH 6.3, a range that fully encompasses the equivalence point at pH 4.79. Therefore, when using methyl red, the color change will occur very close to the actual point of neutralization, ensuring accurate endpoint detection. In conclusion, methyl red is the appropriate indicator for the titration of a weak base such as cocaine with a strong acid like nitric acid.